In 2010, the best computer vision system on Earth got nearly 1 image and 4 wrong. Show it a photo of a dog, and it might answer dog, or it might answer mailbox. This was the state of the art. Machines, essentially, could not see. 7 years later, that error rate had fallen to about 1 in 44, better than a trained human being doing the same task by hand. This is that fall, drawn to scale, the ImageNet challenge, year by year from 2010 to 2017. 1 line on a screen. But every single step down this curve is a research paper, a specific team, a specific idea, a specific moment. The ground moved. And the last step doesn't just end a story about labeling photographs. It begins the one we're all living in right now. A quick note on the metric, because the rest of this hangs on it. This is top 5 error. The model gets 5 guesses per image, and it only counts as wrong if the correct answer is in none of them. The flat line across the middle is the human score, about 5%. Watch for when the machines cross under it. Let's start before the curve even begins, with the thing that made all of it possible. Not an algorithm. A dataset. In the mid-2000s, a young professor named Fei-fei became convinced the whole field was looking in the wrong place. Everyone was hunting for smarter algorithms. She thought the bottleneck was the data, that a child learns to see by absorbing millions of examples, and no algorithm would ever generalize until it could do the same. So she set out to build that, an absurdly large, carefully labeled map of the visual world. Her team took the structure of an English dictionary called WordNet, and for tens of thousands of concepts, dog, strawberry, airliner, they went out to collect and label real images, hundreds of them each, by hand. The scale was almost ridiculous, more than 14 million images, across about 20,000 categories. Early estimates said it would take decades. What rescued it was a brand new tool, Amazon's Mechanical Turk, that let them farm the labeling out to tens of thousands of people around the world. It still took years. When they published ImageNet in 2009, the response was mostly a shrug. A bigger dataset wasn't a breakthrough, it was bookkeeping. But Lee had quietly built the one thing the coming revolution would need, a yardstick big and hard enough that, for the first time, you could actually measure who was winning. She turned it into a public competition. And in 2010 and 2011, the winners, using the best hand-engineered techniques anyone had, sat stuck up here, around 26–28% error. The racetrack was built, nothing on it could go fast, yet. But there's a piece missing from this story, and it's the reason the early years sat so flat. The method that would eventually shatter this benchmark already existed. It had existed in pieces for decades. The neural network, loosely inspired by the brain, went back to the 1950s. The trouble was, it kept not working. It got hyped, it underdelivered, funding collapsed. Twice. People called those stretches the AI winters. By the 2000s, mainstream artificial intelligence had largely moved on. Neural networks were an academic backwater, kept alive by a stubborn handful of researchers who refused to quit on them. Admitting that's what you worked on could cost you a grant or a job. The smart money was somewhere else entirely. So that's the real picture in 2010 and 2011. The racetrack was built, the data was ready, and the one approach that could actually use it was the one almost nobody was funding. The curve sat flat not because the idea didn't exist, but because the world had given up on it, which is exactly why what happened next hit so hard. Then came 2012, and the single largest drop on the entire chart. The entry came out of Geoffrey Hinton's lab at the University of Toronto. Hinton had spent literally decades on neural networks, an idea that had been written off, revived, and written off again, to the point where admitting you worked on them could quietly end a career. His 2 students, Alex and Ilya Sutskever, built a deep neural network, a convolutional network of a depth most people thought was untrainable. And here's the detail this channel cannot resist. They trained it on 2 consumer gaming graphics cards, 2 NVIDIA GTX 580s, the kind of part we put on a price chart in our very first episode. Pause on those 2 graphics cards because they matter more than they look. Training a neural network is, underneath, one thing repeated millions of times, the same small piece of arithmetic over and over, all at once. A regular processor, a CPU, is built to do a few complicated things very fast, one after another. That's the wrong shape for this problem. A graphics chip is built the opposite way, to do thousands of simple, identical calculations at the same instant, because that's what drawing a game frame demands, shade a million pixels, now. It turns out teaching a network to see needs the exact same kind of math, and in 2007, NVIDIA had released something called CUDA, which let researchers run their own math on those gaming chips, not just graphics. So look at the coincidence. for completely unrelated reasons, to sell video games. An entire industry had spent a decade building the precise parallel computing engine that deep learning would need, and driven its price down to something a graduate student could afford. AlexNet didn't just prove deep networks worked, it proved the machine to train them was already sitting on a gamer's desk. Krzyzewski tuned it for weeks in his bedroom. The hardware curve and the intelligence curve, it turns out, are the same story. The graphics chips that rendered video games were, almost by accident, the perfect engines for this math. The result, called AlexNet, won by a margin nobody had ever seen. It cut the error to 16.4%, while the next best team, using the old hand-built methods, was all the way back at 26, roughly a 10-point gap in a field that fought over fractions. One honest footnote: because you'll see a different number everywhere, the paper's headline figure is 15.3%. That version used extra training data and averaged several networks together. The official winning entry on the leaderboard was 16.4. Pick whichever you like, the story is the cliff either way. The room, by every account, went silent. Within months, deep learning went from unfashionable to inevitable. Google bought Hinton's tiny company. Sutskever would go on to co-found OpenAI. The modern era of artificial intelligence has a birthday, and this is it. After a shock like that, the field had an uncomfortable question. Nobody was quite sure why it worked. A deep network was a black box, millions of numbers that, somehow, produced the right answer. That's a great party trick and a terrible science. In 2013, Matthew Zeiler and Rob Fergus cracked the box open. They built a way to run the network backwards, to take what a layer had learned and turn it back into a picture you could look at. And what they saw was beautiful and oddly intuitive. The earliest layers had taught themselves to find edges and colors. The middle layers assembled those into textures. The deeper ones lit up for whole object parts, a dog's face, the spokes of a wheel. Nobody had told the network to do any of that. It built the hierarchy itself, from raw pixels. Suddenly, deep learning wasn't alchemy, it was something you could inspect, debug, and improve on purpose. Their model took the 2013 title. They entered as a startup called fei-fei, and dropped the error below 12%. The black box had a window now. If 2013 explained the magic, 2014 industrialized it. Around a single, almost crude lesson, go deeper, two teams pushed it from opposite directions. A group at Oxford built something called VGG that was beautiful in its bluntness. Just the same tiny 3x3 filter stacked over and over, deeper and deeper. It was simple enough to become the default building block for years. Meanwhile, a team at Google built GoogLeNet. 22 layers of cleverly branched modules they named Inception, engineered to go deep without the computation exploding. Yes, after the movie. The "we need to go deeper" joke was fully intended. Between them, they cut the error in half again, to under 7%. The trend was now undeniable, and it had a direction. Every year, deeper networks, lower error. Which naturally raised the question, how deep can you actually go? In 2015, somebody hit the wall. Here's the strange thing the field discovered. Past a certain point, deeper networks got worse. Not from overfitting, they got worse at the training data too. Stacked too many layers, and the learning signal degraded on its way down, and the whole thing choked. The ladder had a top rung, and it seemed to be somewhere around 20 or 30 layers. A team at Microsoft Research, led by Kai-Ming He, broke it with an idea that sounds almost too simple. Instead of forcing each layer to transform the data, let the data also skip straight past it. A shortcut, a residual connection. So a layer only has to learn the small adjustment it adds. Give every layer an express lane, and the signal stops degrading. They called it ResNet, and they didn't go to 30 layers. They went to 152. The error fell to 3.57%, and that number is special because of this line. A year earlier, a researcher named Andrej Karpathy had done something stubborn and useful. He sat down and labeled ImageNet images himself carefully to measure how a trained human actually performs. His score was about 5.1%. So in 2015, for the first time on this specific task, the machine was more accurate than the person. Now, the honest version, because it matters. This does not mean the machine sees like you do. It means it beat a human at one narrow, peculiar game, sorting photos into 1,000 fixed buckets. Change a handful of pixels a person would never notice, and these same networks will confidently call a dog an ostrich. They had superhuman accuracy and no common sense. Both of those things are true, and the rest of the decade is the field reckoning with the gap. But as a milestone, as a line on a chart that a machine was never supposed to cross, this is the summit. Before we leave the summit, it's worth asking what that line actually proved, because the honest answer shaped the next 10 years. Beating ImageNet means a system can sort photographs into 1,000 fixed categories better than a person can. That is genuinely useful. It is also a very specific, very narrow definition of seeing. These networks learned correlations, not understanding. They had no sense of context or cause, and they quietly absorbed whatever biases lived in their training images. Out in the real world, in cars, in clinics, those gaps mattered enormously, and not one of them showed up anywhere on this leaderboard. So hold both truths at once. On the benchmark, the machines genuinely passed us. In the ordinary common-sense robustness a small child takes for granted, they were nowhere close. The curve is a real triumph. It just isn't the whole story of sight, and the researchers who drew it were usually the first to say so. After the summit, the air gets thin. In 2016 and 2017, the error kept falling, under 3%, then to about 2.25. But look at the curve, it's flattening. These were brilliant refinements, squeezing out the last fractions. The honest read is that the benchmark was becoming saturated. When your models are more accurate than your human labelers, you're no longer measuring vision so much as measuring the noise in the test itself. So in 2017, after 8 years, they retired the ImageNet challenge. Not in defeat, and something closer to mission accomplished. Machine vision was, for practical purposes, solved. The mountain everyone had been climbing was now a foothill. The field needed a new one. And, almost on cue, in that very same year, somebody handed it a whole new range. This paper wasn't about images at all. It came out of Google in 2017, with one of the most confident titles in science, "Attention is all you need." The problem it tackled was language, translation specifically. The established way to handle a sentence was to read it one word at a time, in order, the network keeping a running memory. It worked, but it was slow, and it forgot. This paper threw that out. Instead of reading in sequence, its mechanism, self-attention, let the model look at every word in a sentence at once and learn directly which words matter to which. Two consequences, and they're the whole future. First, it was better. Second, and this is the part that quietly mattered more, because it processed everything in parallel instead of one step at a time, it was a near-perfect fit for exactly the kind of massively parallel hardware that AlexNet had unleashed. It didn't just learn well, it scaled. Pour in more data and more graphics chips, and it kept getting better, with no obvious ceiling. That architecture has a name now, the transformer, and it's the T in GPT. It's the foundation under nearly every system that has stunned people since. The language models, the chatbots, the image generators. The same recipe that conquered ImageNet, depth, data, and compute, had just been handed a domain with no edges. So pull back and watch the recipe escape the lab. The lesson of this whole chart was never really computers can recognize cats. It was something more dangerous and more useful, that if you take a deep network, give it an enormous amount of data, and throw an enormous amount of computation at it, capability reliably follows. And here's the lesson the field actually took from all of this, the one that explains everything that came after. It wasn't a particular architecture, it was a suspicion slowly hardening into a belief that you could get more intelligence simply by making everything bigger. More data, more computation, more layers, no new genius required, just scale. ImageNet was the first clean evidence that the bet paid off, push harder on data and compute, and the curve really does bend. Once people believed that, the race stopped being about clever tricks and started being about scale. Bigger models, bigger datasets, warehouses full of the descendants of those two gaming cards. Every headline system since is that same wager, scaled up until it stopped sounding like research and started sounding like science fiction. The language models writing essays, the systems folding proteins, the image generators, all of it is the ImageNet lesson, taken at its word, make it bigger, and see what it learns. Once people believed that, they pointed it at everything. At Biology, in 2020, a system called AlphaFold essentially solved the 50-year-old problem of predicting how proteins fold, a feat people thought was a decade or more away. At Language, GPT-3, then, in late 2022, ChatGPT, the moment the rest of the world finally felt the curve we've been tracing. None of it arrived from nowhere. Every one of those systems is a descendant of a deep network, trained on a giant dataset, running on a wall of graphics chips. The exact pattern that, a decade earlier, learned to tell a dog from a mailbox. So here's the whole thing on one timeline. In 7 years, machine vision went from getting 1 image and 4 wrong to beating a trained human, and then the same idea stepped off this chart entirely and became the defining technology of our decade. And when you ask what actually made it happen, the answer is humbler than the result. 14 million images somebody insisted on labeling, a couple of gaming graphics cards in a bedroom, and a handful of researchers who'd bet their careers on an idea everyone else had given up on. We tend to talk about AI like it appeared overnight in 2022. It didn't. It came down this curve, one paper at a time in plain sight. Where it goes from here, nobody can draw yet. That line hasn't happened. But this part did. The cost of teaching a machine to see, the people who paid it, and the world it opened, all of it in one timeline.